Well, welcome to week 2 of Catalyzing Inclusive STEM Experiences 365, or all year round. My name is Linford Goddard. I'm a professor of electrical and computer engineering at the University of Illinois. And we're excited that you're here so that we can talk about the goal, the vision, the project that we have, this NSF-funded grant. So I'll go into an overview of what the goals are of this project, and I'll talk about the STEM clubs, which is pillar number 2 of our 3-pillar approach. So overall goal, so the background and the idea behind this is we want to broaden the participation of students from underrepresented groups through year-round technology and engineering-rich learning experiences so that students can build discipline-specific knowledge, they get an opportunity to work with technology, and they can better understand what careers exist in STEM and possible future majors and careers. So for this project, we have a quantitative goal that we talked in our proposal to National Science Foundation. We had a bold vision to be able to have experiences for over 1,000 high school students in the state of Illinois. And so we wrote our proposal in a way that we're partnering with 24 schools. Each school, roughly 40 to 45 students, will participate in these STEM club activities. And this will provide them with a sustained, intensive, hands-on STEM learning experience that builds technical knowledge and ability. And in addition to this, we also are going to work with the schools to have scholarship opportunities for students to come to summer camps at University of Illinois that are focused on engineering, science, math, and so forth. Okay, so in order for us to achieve the goal, we have certain objectives. So the first objective is that we're going to equip you, the high school, middle school, and high school IDEA teams. IDEA is an acronym: Inclusion, Diversity, Equity, and Access. We're going to equip you through this 2-week Summer Institute with strategies and resources so that you can go back and promote your students' interest in and also their pathways towards pursuing a technical career or major in STEM. And we're going to do this by doing this 2-week, 10-day, 80-hour Summer Institute. It's going to teach the knowledge, attitudes, and behaviors, and also provide you with resources and the resources to realize these desired improvements. So part of what you're going to do is have this networked improvement community, and so you're going to be working with each other, not only at your school, but also at the different schools. You'll have this online collaborative format where you can exchange ideas and talk to each other about what's going well and what needs improvement. Your work during the school year is going to include something called Action Research Equity Projects. So Megan Pollock talked to you about it last week. This is going to be your opportunity to test out ideas that can promote equity and access in the classroom. And you'll write up a very short summary of the results. And so the goal is to understand ways to improve STEM education and STEM access. Okay, so that's the first pillar. The first pillar is the Summer Institute that you're currently at, this 2-week program. So week 1 was the discussion about micro-messaging to reach and teach every student. And then this week, we're going to focus on the technical content and really work on understanding what projects can be done in a relatively simple manner, but that are really kind of inspirational and exciting for students to do. So the second pillar is that we're going to work with you, the IDEA teams, to develop, to launch, to fund. We're going to work on the funding part and to sustain, because a lot of times you have great ideas and you put them into action, and then you have to be able to have a model that's going to sustain them. So we're going to sustain these out-of-school STEM club or STEM clubs or academies. Now, these can be during lunch, they could be over the weekend, they could be after school. It's really up to you to figure out which format and which sorts of options and settings works best for you and for your students. These STEM club activities are going to provide unique experiences with engineering design. So the idea of taking a project, starting from conception, realizing a problem, and then applying a methodological approach to solving it, and then constantly improving it. So it has engineering design, it has project-based learning, so you're going to explore, or your students are going to explore different concepts in STEM, going all the way from basic math and geometry to basic science, some physics, and then some more really advanced concepts that a lot of the students here wouldn't see until maybe their sophomore or even junior year. And the goal is to have, as I mentioned, 1,000 students participate in these clubs, so about 40 per school. And it's roughly anywhere between, I would say, maybe as low as 40 to up to 120 contact hours. It really depends on how much additional stuff the students are motivated to do based on their basic going through the curriculum. So the curriculum lays out about 40 hours of material for them to do in these clubs. And then there are a lot of ideas for advanced projects or independent type group type independent work to be able to do even more exciting things. The third pillar of this program is to provide scholarships to 228 students to attend these already existing STEM summer camps. And Dr. Laura Hebert will talk more about the opportunities that are out there through the College of Engineering, also through other departments like mathematics that's outside of college, but they're still related to STEM. So we have a lot of summer camps. The summer camps range from 3 days, the residential programs from 3 days to 5 days. Some of the camps are non-residential, so they're for local students who are carpooling in each day. But in general, they provide these immersive college-like experiences where students get a chance to live in the dorms, go through the cafeteria food, go to class on time, sort of be able to get to that point where they're able to see what is college like and is this for me? So those are the overall objectives for achieving our goal. Okay, so I'm going to put this up, but I'm not going to talk about it in great detail. Basically, the motivation is that the U.S. economy needs people who are trained in STEM. There's many of jobs that are out there. However, our students are not currently pursuing it as much as we'd like. I'm going to put this up, but I'm also not going to talk about it. I'll talk about two of the columns. So the logic model or theory of action is basically what inputs are we putting into the program, what is the structure of what we're doing, who are the participants, and then what are the activities that they're going to do, and then based on that, what are the short-term and projected long-term impacts. I want to talk about the short-term and long-term impacts because those are the most important. So some of the stuff that we want the students to be able to do, we want the students to have improved knowledge of, interest in, and aspirations for careers in STEM, and know what the educational pathways are to get there. We want students to have increased self-efficacy. So we talked about this last week. Self-efficacy is the belief in one's own ability to be able to do a certain task. We also want them to have increased disciplinary specific knowledge and skills. So some of the things that the students will learn are how to work with circuits on breadboards, how to do soldering. Soldering is a skill that when I was going through high school, I had an electronics class and I really enjoyed it, and that got me really excited about building things. In college, a lot of times students go through college never learning how to solder. Even in a department like electrical and computer engineering, it's not a required thing, but it's a skill that's useful as a hobby or as an ability to build and test out interesting things. The third short-term outcome is that we'll have improved educator and counselor understanding of STEM careers and paths. So you as participants will be able to go back to your students and talk to the students about what are the ways to get into STEM, what are the opportunities that are out there. Improved educator and counselor attitudes on who belongs in STEM, and also working as advocates for STEM equity and access. So you as participants have been given some of the skills and resources to be able to communicate with your students to get them excited about getting into STEM. Adjustment of practices by counselors and educators so that they're really focused on addressing the acronym IDEA. Inclusion, everyone is welcome. Diversity, we have participation from all parts of the population. Equity, all students have all students have the resources they need to succeed. And access, the ability for students to have these opportunities. So working on the skill set to be able to promote these amongst your activities. Program impact, effectiveness, and sustainability. So in order for us to have a model that we can translate to other states in the US, so our focus this year is Illinois. We're partnering with 24 schools. Our goal, our long-term vision is that this model will be successful and that we'll spread it to other states in the US. There are many opportunities and many partners that we already have that could potentially implement something like this at other states in the nation. So we want to be able to show that what we're doing has actual impact, that there's measurable outcomes, and that it's sustainable. So the sustainability is probably the most challenging aspect of this. It's going to be different based on different schools, based on different abilities and so forth. We want to publish research results in journals. So we're going to be working with engineering education to be able to say which practices are most effective at improving student knowledge or student self-efficacy or teacher or counselor attitudes and behaviors and so forth. And then we're going to disseminate best practices at regional and national conferences. So those are the short-term outcomes. Those are the things that we're looking for being able to do in the next 2 to 3 years. The projected impact, sort of what do we expect out of this overall program, we want students to be exposed to content and career opportunities that likely they would not have known about otherwise. We want more students participating, or more of the participating students enrolling in advanced high school science and math classes. So one of the measures that we'll use to see how effective STEM club activities are, how effective our Summer Institute is looking at the enrollment data to see are students enrolling in these advanced math and science classes. Are the schools more effective in identifying and addressing behaviors, policies, barriers that contribute to inequities in STEM? So there are certain things that we do. We talked a little bit about unconscious bias. We talked a little bit about sort of equity, being able to have everyone have the resources that they need to succeed. Are there things that are systematic in the schools that we work with, or that in schools in general, that create some of this inequity that exists in STEM? Are schools able to serve underrepresented students in STEM more effectively? And then I mentioned that our goal is to spread this idea through other states in the US. And the final super goal is that we'll have a larger and more diverse STEM workforce. So this is sort of the theory of action. I didn't get in the first 3 columns, but the outcomes are the things that we want to think about. Okay, so now let's talk about the STEM clubs. So the STEM clubs are something that needs a lot of thought, needs a lot of development. And so all I can offer is sort of some general guiding principles on how the STEM clubs should interact and operate. The first is in everything the STEM club does, it needs to think about and strive for the goals of IDEA. So in everything it does, it needs to be an inclusive environment. Students from different backgrounds need to feel welcome. What they say needs to be heard by their teammates. And so promoting this sort of behavior in the students is something that as facilitators will be something that you'll work on. I talked about diversity, equity, and access already. So student recruitment, as teachers and counselors, your role is to get students excited about this project, get students recruited to be part of the STEM club. And you really need to make a concerted effort to get students from underrepresented groups. So students from underrepresented groups in STEM include women, students from ethnic minorities, so African American, Hispanic, Native American, Native Alaskan, and so forth. Low-income students, so students who typically will not have resources to be able to go to really cool STEM summer camps and so forth. And students who are first generation, meaning that their parents did not complete college. So the goal is to recruit students from these populations at a higher level than if you just randomly picked students. So one example, so I'm going to give this as a message. One way that you can do this is to do the micro-messaging ideas that we talked about last week. So talk about strengths of the student, encourage them based on positive affirmations. So things like, you see a student, Keisha, you have a passion for learning and you have a passion for helping others. I think you'd enjoy being a part of the STEM Club because there's an opportunity to learn through projects and also to do something for your community through a capstone project. You also have a very welcoming personality. You get along with people very nicely. You'd be a natural leader of the club. So the target, or the goal of that statement, is to get the student excited about being part of it and to be feel like they have an ability to do the things that we want them to do. The target for each club is to have 40 members. So as I mentioned, we have 24 schools, roughly 40 to 45 members. That's the goal. It's not something that we're going to hold you to exactly, but the goal is to have roughly 40 members or more. And then we want the representation within that group of 40 to significantly exceed the demographics of the school for that group. What I mean by that is we want to have, ideally, at least 20 female students so that we have a critical mass. There's a lot of theory about how students interact in group settings, and there's a number that I have in my head that if 30% of the students are from a certain affinity group, they don't feel like they're singled out and they don't feel like they're different than the other students in the class. And so getting to that critical mass of 30% or even better to 50% will really help students from underrepresented groups. Now, some of the schools that we're working with, it's almost 100% minority, so you can't significantly exceed 100%, but if you're at high level, that's good too. Okay. Second set of guiding principles. Probably one of the most interesting ideas is that the club should be led by the students. The club should be viewed as an extracurricular activity that students are leading, that they're motivated by, that they're governing, that they're controlling, and so forth. So an informal learning opportunity that provides students hands-on experience with emerging technologies while at the same time developing fundamental skills and interest in STEM. So what is your role? So your role as teachers and as counselors and as activity coordinators is to be facilitators. So there's a common statement that I've heard when you're working as a facilitator. If the students are stuck, remind them that they should talk to each other. Remind them that they should collaborate because other students, this sort of peer-to-peer learning, is a very powerful model. I don't know about everyone in the room, but when I have to teach something to someone else, I learn it a lot better than if I had learned it just in class. So the idea of peers helping peers, teaching each other how to do certain activities and certain projects is very important. So when students are stuck, encourage them to at least 3 other students before they come to you to ask for the answer. And you're not always going to know the answer. So a lot of this is also going to be encouraging them to use online resources to find information to the questions that they have. The third part of leading the club by the students is that there should be opportunities for leadership. So we talked last week, or I should say, the admissions group talked last week about extracurricular activities, especially as they relate to potential majors. That's a very important point in the admissions process. And so the club offers many leadership opportunities. Minimally, I can envision, and maybe each school has slightly different structure, but I can envision the need for having a president of the club, having someone who's equipment manager, someone who's treasurer. Now the equipment manager and the treasurer could be the same person, or it could be 2 different people, and someone who's in charge of membership, who's keeping track of which students are part of the club, and also being the liaison with the university researchers as we're working with the optional part of the program, which is the educational research. So those positions definitely should exist. There should be some election, probably. Maybe in the first, to get going, the facilitators will nominate certain students to be in these leadership positions. Now there's also an option to add additional leadership positions. So a lot of the projects, it'll be good if one student really knows how to do that project and can teach others. And so you can have technical project leaders who are basically the experts at each of the individual projects. There's an idea of having a director of community outreach. So when you're thinking about, or the students are thinking about the projects that they're going to do for their capstone project, they need to interact with the community to find out what the needs are, what projects are going to be beneficial. So someone who is leading that effort would be a good thing. There can be a social chair, there can be a publicity chair. So the publicity chair is going to document the stuff that the STEM Club does. They'll interface with us. We can put stuff up on our website as to what projects students have done. We can coordinate with getting local media to potentially cover some of this. And then we can work on press releases. So the University of Illinois has a very good communications department, and the students and their projects and their messages can get out to a very large audience if we work together. So these are sort of the positions that I see. You may realize, oh, our school has a specific need and we need another person to do a certain task. And so that could be another leadership opportunity. One of the interesting things with the projects is that it allows for flexible scheduling. Now, most of the projects can be done in any sequence. So if there's students who are really excited about a topic that's in Chapter 14, they can start with the topic in Chapter 14. Most of the projects can also be done at home. So if there are motivated students who have other commitments, like they're in varsity sports or they're doing band or something else, it's possible for them to take the supplies with them home and work on the projects at home. Now, there are a few things that they can't do at home, like the soldering and maybe some of the stuff that requires the equipment, but most of the activities are portable and can be done outside of school time, outside of school facilities. Okay, last point that I want to bring up with the structure is that there's a curriculum and there's a capstone project. So the students will build self-efficacy and learn technical skills by completing STEM projects of increasing difficulty. So the idea of, I can do this because I've done something that was similar to it previously. We're going to build up their self-efficacy by this sort of approach. And the projects were based on a summer camp that I helped to develop called Girls Learning Electrical Engineering. And during the week, the students in the camp will build all of this stuff within about 40 hours of the week. And they sprinkle in some tours. So it actually can be done in very short time. Now, in the STEM clubs, we want students to have enough time to really understand and appreciate. So one of the things that was missing, I would say, in our summer camps is with only a week and with many, many activities we want to do, we rush in a lot of things, and the students don't always fully get a chance to appreciate, to think, to reflect on the activities that they do. So in the STEM club format, let's say the students are meeting twice a week for an hour or once a week for an hour. They have that opportunity in between meetings to do reading, to understand more of the material, to look up stuff that's on videos, to talk with each other, to reinforce that learning. In addition to the curriculum, which is very structured in terms of the projects that the students do, there's also unstructured work. And so throughout the years, we'd like the students to work in groups and use the principles of engineering design to think of and then to complete a capstone project. Ideally, the project will positively impact their community or a group that they're passionate about. And so these are the two, I would say, key elements in sort of the STEM club. Now, there's a lot of things that the STEM club can also do that I don't have on these slides. So one possibility is that they do a journal club. So they subscribe to some of these free scientific or math or engineering related journals that are targeted at the high school level. And then they read articles to learn more about specific topics, and they can discuss it with each other as to, oh, did you read this article about how the National Science Foundation is really excited about and is doing a lot of work in quantum? What is quantum computing? What is that about? That's not currently covered in what we're learning. Can I go and can we learn more about this new hot initiative? So looking at these sorts of engineering or STEM related journals that are or magazines that are at the appropriate level, and we'll have a list of them on our webpage, could be one activity that the club does. Peer teaching can be another thing. So let's say that students who are in STEM club, they're really excited about what they're doing. They want to recruit more students to STEM club, so they hold a workshop. Everyone at the school, you're invited. We're going to come together and we're going to build something cool. And so the students of the STEM club can then transfer their knowledge by teaching, which reinforces that, on other students at the school. Maybe it's part of an assembly, maybe they're doing a presentation, a show and tell, an open house night, these sorts of things. So I'll open it up for questions. It's interesting being in this formal recording mode. It feels different than if I'm just talking to you.
I just want to
Sure.
make a comment. Dawn, that everything you're saying is so consistent with what I strongly believe in. My daughter is a civil engineer, and she's only a civil engineer because I kept telling her the sky's the limit on science. She was discouraged by a lot of people. In fact, her major in high school was art. And somewhere inside of her, when she was in college, she just decided, you know what, I kind of think I like some of that kind of stuff. But my point is, you are absolutely right. There are a lot of kids and people who don't even know that that part of them is in there. So yeah, I'm happy about everything that you're saying.
Okay, thank you. Yes, Lemon.
This is a question. So what's, I think, unique for Liz and I is that we have on-campus registration that starts tomorrow and Wednesday.
Okay.
But we'll be here, so there's table and booths that they're going to set up.
Oh.
But we can't take any of this there because we'll be here.
Do you have a friend at Urbana that we can give information and material to put into the booth?
Moving forward, what we do have the opportunity to do is to set up said booths and do these things at the beginning of the year, started them in the lunch periods and things like that. So moving forward though, with the curriculum, what is like a time frame as far as getting kids signed up into the club and just getting the basic, the initial movements of what your club is starting to look like? What's the time frame that you all would like to have as far as communication from us? Hey, we got right now 19 kids who've already committed, and we feel like we're ready to get started doing this and bring other kids along. Or is there a time, just
Yeah. I mean, I would say think about how the other clubs at school operate. So yeah, day one they're not doing activities, but within the first, they're already established. Yeah,
which is
so that's
why
a good.
Being here is important, but then strains our ability
to recruit. Yeah. So, sorry, you wanted to comment on that?
I'm feeling the same concerns that Lamont is there. Going 0 to 100, and it looks like you're presenting this as a one-year project. That you would have a curriculum, that you would have a capstone, that you get up to 40 kids, you have all these elections, and it's. I think it's more realistic to look at it as kind of a multi-year thing, and that you wouldn't necessarily do all the projects in the first year, but you would do some. You wouldn't necessarily get to 40 in the first year, but you'd get to 20, and then the next year maybe to 40. But I guess just like to get your thoughts on that. Is if we look at it as this is all got to happen in 1 year, I think we. I know if I were a student and I felt like I didn't have time to finish the project because meeting time was too short, and then I was just told, okay, go home and finish it on your own. And I think we're not going to get the buy-in that we would if we had a sense of we're going to go at whatever pace it's clear that the students are ready to buy in at. We're going to build that this is an idea of ramping up at a pace that's sustainable rather than, okay, we've got this schedule.
Yeah.
And we've got to get these
So,
people elected. Okay, two people show up the first meeting. Okay, you're president, you're this. Now you've got to recruit the third person to be the third leader. And you're just not necessarily
Yeah, so let me,
Nothing.
yeah, you're bringing up a lot of points, and I'm agreeing with everything that you're saying. So first point, and I want to pause you because I want to be able to answer and not forget all the points. The first part, multi-year. Oh, okay. So let me mix in the two responses. Okay, and if I miss something, then I'll come back. Multi-year, yes, we definitely want to do multi-year. So this is not a one-year project and then it's done and the clubs cease to exist. We do want to ramp up and we do want to go at the speeds that the students are able to sustain. So the projects and so forth, although they're envisioned to take a year, like spread out throughout the year, there's nothing that forces us to do everything in a year. It definitely needs to be, as I mentioned, led by the students, and so the students should dictate the pace at which they're going. The way that we're going to break up the curriculum, there's going to be 2 volumes, so volume 1, volume 2. If they start on volume 1 and all they get through in the first year is volume 1, that's perfectly fine. Year 2, they can do volume 2. There's other curriculum that other faculty are developing as well. So it really depends on the speed at which the students are going. And we definitely don't want to frustrate them. We don't want them to have like 40 minutes, they put some parts together, and then it's like a quarter of the way done, and they're like, oh, now I have homework and I have to take this home. So it definitely needs to be structured in a way that the students are able to go at their own pace, and not necessarily we're going to complete everything that's here, we're going to go all the way through the projects. Okay, so coming back to some of Lamon's questions. So how do you get students into it? How do you recruit students? What's that?
Kind of the time frame.
The time frame.
How I get them.
Okay.
I just want to make sure.
Oh, the
that
time frame of
our
when they're,
recruitment and
yeah,
setup
yeah.
processes are in the line of whatever you
Yeah,
want time
so I will say you can take your time. And the reason is that we actually don't have all the parts to send to the schools right off the bat. And so what I'm envisioning is that I don't know if you can carry, well, you're local, but I don't know if the people in Chicago can carry with you one of these medium-sized kits. So we will package enough activities for like about a week's worth of material in one of these kits. So a week being like 4 or 5, I really should say sessions. It's really about 4 sessions worth of material in one of those. And hopefully you can take that back with you. And then whenever it's convenient for you, you can do that activity. Sometime in, I would say, mid-September, we'll have everything, maybe even late September, we'll have everything ready in terms of materials and supplies and so forth. And that's when I'm planning to go to the schools to deliver the stuff. So you actually won't be able to do very many of the activities until then anyway. So there is going to be, yes, there's definitely a lot of time.
club set up.
Yeah.
Be talking about this is what it looks like, this is where it's coming from. Okay.
Yeah, and I agree that the first couple of meetings, it's sort of a balance. You want to get them excited, so you want to do something that's technically related, some sort of thing that they're able to put their hands on, but not necessarily try to like, okay, and now we're going to read 2 chapters, or what I assigned with you, like you're going to read 6 chapters on the first meeting. I have a few ideas in terms of which topics and which projects can be done with like minimal preparation. So small amounts of materials, you can do it at any time, any location, not a lot of setup involved. And they're reasonably engaging, not as cool as all the other projects, but they're really, really short. Now with recruiting and like when you're gonna get the students in, when they're gonna get elected and these sorts of things, again, that's something that you need to decide. So I would think that you set up your booth first couple of days of school, or like I guess it's now, and get students the message as to this is an opportunity that's going to be coming down the pipeline. Look for signups for this club. We're going to be meeting Mondays at 3 or Tuesdays at noon or something like that, and give them an idea as to what the time commitment's going to be and sort of what the timeline is going to be. That this is not something that's going to go up 100% right at the beginning. Okay, circling back to Terry's point about 40 students and going from ground 0 to ground 40. We want 40 students total throughout the project per school. So if you have 10 the first year or the first semester, and then second semester it's 20, and then by second year you're up to 40, that's perfectly fine. I think they should be unique students, like you shouldn't double count a student from year 1 into year 2, because we want to claim that we've interacted with 1,000 students. Now there's some other questions that I missed that I may not have answered.
As far as focusing in on the student-led, student-facilitated, your thoughts or opinions on within the club creating like student blogs where they can communicate with each other, you know, via an electronic blog, they can post. From where I sit and the work that I typically do, I feel like that when students are broadcasting the good news of things that are happening, it has a far more reaching effect than if it's coming from me.
Exactly. So the other part, I guess I didn't mention, is that we want students to video what they've done. So it's like, today I've built some, and you're not going to have problems getting students to video stuff and put it on YouTube and so forth. But like today, we were doing this activity and we built this circuit that adds up numbers and it displays the results in light. And here's how it works. And we did this and we designed it first here and then we drew this. And like having them talk about it and having them record it in digital format where they're talking and they're doing video, that's definitely an important point. I should add that into my slides, but it's sort of the idea of the publicity chair. The publicity chair's role is to basically videotape and to send blurbs out, maybe write the blog, these sorts of things. Yeah, so communication, so not only are they going to communicate with other students at their school, we're a network set of schools now, and so students at Chicago Vocational could be sending stuff at Smith, could be sending stuff to Muhammad and so forth, and you can all share. Basically, you have the same parts, and if a set of students come up with something really cool to do, definitely share it with the other students in the other schools. Yeah. Other questions related to that? Did I capture everything? Did I miss parts of the question? Sure.
With this being STEM, is there any provisions as far as you offer resources, whether it's suggestions on how to maybe go about purchasing things, or you all have to debate?
Yeah, so let me, so that's going to be in the second part of the presentation. No, it's a very good question. Any other questions before I move on? Okay, so the second presentation is precisely Donnell's question. So where did that window go? Okay, so the resources that each school will be provided. So I mentioned this at the end of last week, but we are sending roughly, I think it's $3,300 now, $3,300 worth of resources and components and so forth to each school. So this is in the basement of this building. This shows 4 of the large size containers, 12 of the medium and 6 of the small, and a piece of paper just to see sort of the scale. There's also parts that don't fit into these containers, and there are also textbooks that are going to be shipped separately. So each school is going to receive these set of supplies, and the set of supplies are so that students can follow the curriculum and do the activities. The assumption is that there are 40 students per club. Now, there are sort of equipment and hardware, which is sort of fixed number per school, and then there's what I call consumable supplies, so parts that go into your circuit that you're going to solder, and the students are then going to take home to their parents and show off and so forth. So we actually provision for 50 for the consumable supplies with the thinking that, okay, you're going to put stuff together, things are going to break, so you have backups. Your school may have 43 students, it may have 48 students. There's still a tiny bit of wiggle room to be able to fit it in. Now, if your school somehow has more than 50, let me know. The consumable parts are probably the cheapest parts of the kit or of the kits, and I would say it's about $15 or $20 per student in consumable parts. So it's not too expensive, and it's actually good for us if you have more than 40 students. So that's a healthy, a club that looks like it's going to sustain itself if you have huge student participation. So just let me know if you are above the 40 student number. We can send out individual sets of consumable parts. Okay, so what is included in this? All right, so this is going to be a long laundry list of stuff. So the storage. plastic bins. So we have 6 of the small size bins, 12 of the medium, 4 of the large. There's going to be Ziploc bags, padded bags, anti-static bags. The bins are going to be labeled on 4 sides and also on the top. This will help the equipment manager or whoever's going to be doing the inventorying keep track of knowing which components are supposed to be belonging to the school and the club and always staying at the school, and which components are given out to students to take home. So there's quite a lot that the students are just going to be given, and they're going to basically own it. So 4 large, 12 medium, 6 small. These numbers are subject to change. We're almost done with the inventorying in terms of like receiving everything and kind of seeing how things fit. We may need to increase the number of certain types of bins. And I mentioned I'll put these slides up or share them with everyone, so you don't have to worry about taking pictures. We'll send these out. Okay, so bin number 1 and bin number 2, general club supplies. So stapler, 7 scissors, 4 highlighters, 6 rolls of tape, 12 packets of Post-it notes, 2 spiral notebooks, a pad of engineering paper, 12 sheets of construction paper. All this belongs to the club. It's supposed to be shared use. Student tools. Each student will receive a multifunction pen. The pen will have a screwdriver, Phillips and flat, inside the pen. The back tip of it, let me use the mouse so that, I gotta switch into, is it this one? Laser pointer, okay. All right, so the back tip of it is actually a stylus. There's a Phillips and flat screwdriver. There are rulers on the side. There's a level in here, and it works as a pen. So a MacGyver tool. And if everything goes correctly, say it again? Yeah, if everything goes correctly, it'll be nicely branded with ECE Illinois. We're still working on that part, though. The first kit for projects. So there's going to be a project that Maddie's going to talk about next. It does alternators and generators. So it has a spool of magnet wire, 12 ceramic magnets, a pack of paper clips, and separate from this, but in the same box, it's a separate activity. There's an activity on algorithms. So there's a deck of cards of a game that I invented called Oracle Sort. We'll play that tomorrow, so you'll kind of learn about how computers sort things through this card game. The overhead projector and optics box. So this is bin number 3. So there are 12 lenses, 4 that are 5 centimeter focal length, 4 that are 10, 4 that are 15. Flashlights, so a pack of 10 flashlights with batteries. Laser level. The reason it's in red is because I haven't finalized exactly which one we're going to use. I tried some out and I wasn't really excited about how they're working. So that one is still to be determined. There are blocks. So for the optics module on refraction, there are these blocks that students can measure and learn about how light bends at an interface. There's going to be these 9-inch long tiny rods so that they can look at total internal reflection. And then there are going to be these printed sheets. These activities are going to be sort of a very simple explanation of engineering design by having the students do this cutout. So there's going to be cutting and folding and stapling. And they're going to build something where they can hold a flashlight, a lens, and a transparency, and they can project light onto the wall. So we'll talk a little bit about how this relates to engineering design. Next set of bins. So bin L1, M4, M5, M11, M12. Probably the most extensive set of components. So in these bins, there will be 10 digital multimeters. So a digital multimeter is a device that can measure voltage, current, resistance. It can check if 2 things are connected. It also tests batteries. It can measure DC voltage, DC current, and also alternating current and alternating voltages. This particular model is typically used by mechanics when they're troubleshooting inside the car. So I think it can go up to, I forgot the exact voltage, it might be 500 volts, but basically it's a really nice digital multimeter. Spare fuses, so if students do things incorrectly, they blow the fuse. And that's a very common error that happens when they're doing this lab. So a set of 5 replacement fuses. White protoboards. So the protoboard is a way to hold circuit components together as you're prototyping. So each student will get to keep their own protoboard, and this will allow them to build circuits throughout the year. Bags of wires. So these jumper wires connect different pins on the protoboard, and so there's going to be Ziploc bags with 1,200 pieces of wire. And so how you'll manage that, it's going to be an interesting experiment. There'll be bags of bags, and bags of bags meaning that there'll be a large, maybe gallon-sized Ziploc bag. Inside that bag will be snack-sized bags or quart-sized bags or sandwich-sized bags, and inside those bags will be things like 50 resistors of a specific type and 50 capacitors of a certain type. And there'll be like 6 or 7 of the different types of resistors and different types of capacitors, and it'll be very important for whoever's the equipment manager to know what the parts are and which things they belong to, because what will happen is if you open up everything, it's going to be a nightmare keeping track of all these components. Other electronic parts that are included, so AA battery clips, LEDs, various small components, lots and lots of batteries. So each school is getting 100 9-volt batteries, 200 AA batteries, 40 AAA batteries. The students are going to keep 40 of the, so with 40 students, they're going to keep their own 9-volt battery and 2 AA batteries because they need it to be able to power their 2 main circuit projects. Alligator clips and 9-volt battery clips. So as an example of what I mean by bags of bags, so Maddie created this sheet, and we're debating exactly how we're going to distribute this. This may show up inside the textbook. It may show up as a separate sheet. But the idea is that you somehow have to distribute all of these discrete components to each student. And so basically, each student gets one resistor that has a certain color, and then one resistor that has this other color, and so forth, and LEDs and so forth. So the idea to keep track of all this, because you're just going to have tons and tons of parts, we're going to have this printed sheet. You're going to carefully distribute like items one at a time. They're going to tape it all down on a sheet of paper. That way they know this is my stuff for my particular project, circuits number 1. These are the components that I need. There's going to be other projects that they have other components for that you don't want to open until they're actually doing that activity. So very easy to mix these parts up. Now you can figure them out eventually. It's just very time consuming. Okay, next set of bins. So soldering. As I mentioned, soldering is a very important technical skill that really stimulates students' interest in electronics and in engineering. It's done a lot of stuff when people are building like robotics, when people are building their own circuits and so forth. So what's included? So 3 soldering irons. So the soldering iron is here, spare tips, and spare sponges. We'll talk about how to solder a little bit later in the week. Helping hands, these are things that are going to hold the circuit boards while they solder. 4 rolls of solder, 10 pairs of safety goggles. The idea is that you'll have roughly 6 students working on soldering, maybe even 9 students working on soldering at the same time by rotating. So it's like, let's say that we have 1 soldering station here, and then you have 3 students. They're all wearing their safety goggles to be able to protect them in case of, so the concern with soldering is that if you like flick something, you can be shooting hot metal into your face, so you wear safety goggles. It also generates a little bit of fumes, and so for some people, wearing the safety goggles is a way to keep that fume stuff out of their eyes. So imagine that I have 3 students, they're all wearing safety goggles. 1 student is currently like putting components into their circuit board and clipping it on so that it's being held in place so that they're ready to do the solder. 1 person has done that already, and they're like so soldering is the process of permanently attaching components to a circuit board by melting metal so that it fuses together. So like you can have 1 person who's soldering and actively doing stuff, and then a 3rd person who's like looking for components or measuring something at the same time. So they'll be kind of rotating. Yes?
Do we have the magnifying glass that also comes along with the soldering because the
Yes.
parts are so small?
Yeah, I'm trying to get the one that has the magnifying glass. I'm running into an issue right now where the vendor that I want to buy from, they can't do tax exempt status, and the University of Illinois can't allow me to purchase anything unless it's tax exempt, so I'm working that one out, but just a minor thing.
I'll ask,
Yeah.
the shared aquarium, because, with the underwater robotics, we have the one with the magnifying, so that I'll try to send a quick email to there, ask, who did he use to get the magnifying glass?
Sure, sure.
One real brief question. For the sake of middle schoolers, the younger kids, particularly sixth graders, is there such a thing as some kind of safety gloves that kind of cover them if they slip?
It's, I don't know of any. So yeah, so soldering, I mean, you're working with soldering irons that are 660 Fahrenheit, so even hotter than curling irons and so forth. We do use lead-free solder, so that's one good benefit. In industry, people use leaded solder. The safety gloves and so forth to protect their hands, I don't know of any in particular. It's not common when solder. To use gloves, yeah. It's not common, but it's something that we can look into. Yeah, I think the challenge with gloves, so if there were heat-resistant gloves that don't feel like anything, because you don't want to affect your dexterity. So that's something to look into. Okay, so safety goggles, solder suckers. So if you make mistakes in soldering, there's something to remove the melted metal, so solder suckers. There's also brass wicks. So solder sucker and brass wicks. These are to undo soldering. 2 spools of wire if you need to make additional connections besides what's on the board. 2 wire cutters per club, 5 wire strippers. Okay, so the first big project is the LED calculator. So the LED calculator, what it will do, you will have, or the students will have switches, and the students will represent numbers in binary as high as 3, so 0 to 3. They'll add these numbers together, so numbers from 0 to 3 plus 0 to 3. They'll get a result that's somewhere between 0 and 6, and they'll display the result in binary using lights, using LED outputs. So over time, so when we originally created this activity, everything was done on a protoboard. And it actually is a very complicated circuit to do on the protoboard. And so what we've done is we've taken the input and output parts and we've made our own printed circuit board with surface mounted components. So we have pre-assembled circuit boards that have pretty much everything except for a few things that you have to solder on, which handle the input and output. So take that plus a protoboard, and that will build this LED calculator. Some of the other things that we've run into, so the parts that they have to solder are these header pins and then also a battery clip, and then they're going to plug these integrated circuits into their protoboard, and that's going to make the LED calculator. And then there's going to be a lot of jumper wires that they have to wire outputs from and to, and there's also a part that they have to do on the computer to understand like how they're going to create their circuit. So some of the things that have gone wrong in the past, sometimes these ICs fail, and it's very hard to debug a circuit when that happens. So we're going to include this logic gate tester, so it's electronic equipment that it can just check to make sure that the circuit is working correctly. It can also test transistors and so forth. And sometimes when you place the IC into the protoboard, it's hard to get out, so we'll give you an IC extractor. The second main project, and this is in the advanced, so I would say LED calculator is sort of the end of volume 1, beginning of volume 2. The FM transmitter is definitely going to be in volume 2. So this was actually the original project idea behind the STEM clubs, or behind the STEM summer camp. We wanted to teach electrical and computer engineering from the viewpoint of the cell phone. So a cell phone has in it a transmitter, it has a receiver. So we wanted to replicate a circuit that can do the transmit function. So what the students will build will be a tiny circuit that allows them to talk into the microphone, broadcast their voice as a FM radio wave, and then someone somewhere else can listen to them on a radio and pick up their signal. So circling back to the cell phone idea, so the STEM Club overall, it explores different aspects that are all related to the cell phone. So the optics that goes into like the camera can be understood from some of the activities. The signal processing, the compression, the power and energy, basically lots and lots of the topics that we cover can all be circled back and discussed in terms of something that they use every day, which is a cell phone. So there's a set of parts, which is in this list here. And as I mentioned, you want to keep these parts sealed until you're ready to do this activity so that you don't mix them up. One FM radio per class so that they can debug. These tiny oscilloscopes. So an oscilloscope is actually a really expensive, really sophisticated piece of equipment that you typically would see in a research lab. So my lab has one that's worth, I think it's $40,000 is how much it's worth. The teaching labs probably have the $10,000 model. This one is a really cheap one, so all it has is an analog to digital converter and a screen. It's around $30, so amazing what you can find on eBay. And then 9-volt battery clips to be able to power the oscilloscope. The communications and signal processing project. So this one, they're going to be listening to how sounds get modulated. So they can play sounds of certain frequencies, they can listen to it, they can hear how compression works, they can visualize how signals that are modulated in terms of amplitude or in terms of frequency look in the time domain and also in the frequency domain. And in order for this to be a hands-on activity, instead of just having computers, we want them to interact. And so the headphones allow them to hear, and then there's a microphone built in, which allows them to record their voice. And for some computers, the 4-prong, so I'll say that this is non-brand name headsets, but the 4 prongs sometimes aren't compatible with all computers. So if the computers have a separate microphone and headset interface, there are these splitters that allow the conversion process. In the advanced projects, so outside of the curriculum, so there's the curriculum, which, as I mentioned, roughly 40 to 60 hours, maybe even longer. There's what I called open-ended projects. And these open-ended projects, there's one that's going to be on microscopy. So there's something called Foldscope, which is an origami-based microscope where students will basically put together lenses and LED illumination and so forth. And it comes with slides with biological samples and so forth. They can see under magnification with this very low cost microscope. And they get to keep their microscope. So it's designed to be something that students can, so not me designing it, but the company that provides this, the intention is that every student can have their own microscope and they can take samples from around their house or around their garden and prepare it onto slides and look under this tiny microscope. There's going to be printed circuit boards for students to prototype circuits that they're interested in. There's a bag of advanced parts, typo, for advanced projects. And then each school, there's one Arduino. So I know that some of the schools have Raspberry Pi, some of the schools have Arduino. Merge those into these sorts of activities, provide these opportunities for students to do these. So these open-ended projects, there's no curriculum for. There's a lot of online resources. So students in the club will receive a set of parts and they'll say, oh, what is an LM555 chip? And they look online. Oh, it's a timer circuit and I can build something that turns on and off and flashes and does cool stuff with it. So they'll look through and see sort of what's there and then think about what they can build from it. Packaged separately, a general purpose toolkit, so your typical hammers, screwdrivers, tape measure, and bits and so forth. I'll ship separately to the schools directly textbooks, so each student will have their own copy of the textbooks. The goal is to have Volume 1 and Volume 2. Volume 1 probably sometime in late August, and Volume 2 sometime in maybe November or December. But again, you'd go at your own pace. And then finally, these last two things. So these are the ones that I'm considering. So the laser level for the optics project and the helping hands for the soldering. But maybe, Anita, did you have another suggestion? Is it like that helping hands, or does yours look different? For the soldering, this helping hands.
It's with the hands with the clips on it, so that you don't
Okay.
have to.
Yeah, I don't know if you can see, there's
It has
this,
a lens.
yeah, there's this magnifying glass
It's
here.
magnifying
So it looks
glass.
like this, or it looks different than
It
that?
looks like that.
Okay, so that's the one that I can get, and I just have to resolve the tax story. Yeah. All right, questions on this?
So they're gonna ship these kits out, or for those of us who
So my,
have a means?
my plan, and it's a crazy plan, as an engineer you always have to have crazy ideas, because shipping is so expensive.
Something about delivery.
Yeah, because shipping is so expensive, my crazy plan is to rent like a U-Haul type cargo van and have ECE shipping help me load everything up. And then one day during the year, we coordinate among the 5 schools, and I drive with someone else, and we go school by school and deliver stuff. So that's the plan.
Or
I don't know if
you
it'll
need
work.
someone to be away from their building for a while.
Yeah, I can recruit you if you want
I
to.
can get the van, bring it over. Yeah, we'll
Okay.
come over there. I'll be in strict coordination. That could be a good off-campus based activity.
All right.
Textbooks, are you
Yes.
gonna ship those?
So those are going to ship direct because those would be ordered through Kindle Direct Publishing, and so I can pick where I ship it. So I'll just ship it directly to the school. Yeah. So I'll need to collect shipping addresses from everyone. Yeah.
Do you know how soon you have the kits ready?
So we're missing parts for certain activities. So basically, I started ordering in late June, early July, and I'm used to 2-day delivery, and it's like, oh, this will arrive in a month, and you're just like, oh. So right now, there's certain kits that are done. There are other kits, I would say the majority kits, they're all missing like some component. So I believe based on the shipment schedule, everything should arrive, or I should say enough should arrive that I can do a delivery late August, early September.
Okay, I was gonna help you out August 19th, I'm moving my daughter down here.
And take that one back. Okay, we'll coordinate with each school as to optimal times. I think there are a few things where it's like if the majority of stuff is ready, then I can do stuff like that. And then if there's just a few other things, then I can ship that separately. Yeah.
Are there like the lessons or particular like steps attached to the bins with the equipment, or is that?
It's in the book. So the book says like the project on FM transmitter. It has a parslets. It says what's needed for it, and then you have to cross-reference what's listed in the book with sort of what's on these slides, which says which bins are needed. So basically, if you're doing FM transmitter kit circuit project, you would need to pull out bins M8 and S4, and then like within that, then you have to go to the book to realize, or look at the sheet of paper as to realize what parts go into that. Yeah. And to do FM transmitter, you also need soldering, and you also need some other stuff. So it's explained somewhere else as to additional things. Yeah. Other questions? Yeah.
Each activity, you will have a video to.
Most activities we will. So the plan is we're going to record today, tomorrow, and half of Wednesday, and that will cover almost everything in terms of the activities. And so the lab assistants, myself, we're going to record as we walk you through these activities. And then we'll clean it up a bit and post it online so that students can view it and so forth. There are a few activities that we're not planning to record, and those are sort of like, after you know the basics, now it's the point where now you're wiring things together. So maybe we might have a short snippet. This is what it looks like at the end, and this is what I did to make it. Or maybe you'll be the one who explains, yeah, this is what I did, and these are the parts that go in. Other question?
I know you mentioned maybe talking to some people in the building on some days or whatever days you're going to drop off the equipment. Is that something that you wanted to do, or you were just saying that
If it's possible, and if your school is interested in that, then yeah, I can do that. So the idea is just that when I go to drop stuff off, if there are people who want to meet with me and talk about like the vision of the STEM club and what's necessary to move forward, or if the students want to interact, then yeah, we can do that. It's really up to the school as to what they want to do. Yeah.
So as soon as you get those.
Yeah. If you want me to come in and say, I'm an engineer and this is how I got into my field, I'm more than happy to do that while I do the delivery. Yeah. Yes.
So as you progress with this program, year 1, year 2, and year 3,
Mm-hmm.
will you be adding new projects?
Yeah, so again, with PACE, we have to see how year 1 goes with the different schools. So if at the end of year 1, everyone's on volume 1, then it's like, okay, well, year 2, we do volume 2. There are faculty at Illinois who are interested in developing content in closely related areas. So there are people who are in material science, mechanical and electrical and computer engineering who've talked to me, who've asked, I'm writing this proposal for this other grant and my research is in this. Can I develop something related to what you're doing? And can we get it out to the schools? And so we'll see how that pans out. That's sort of a year from now, we'll know whether these things exist and what they plan to do with it. But yeah, one of the interesting aspects of this grant is that it can act as a springboard for other projects. So small projects that faculty have that they may not have the infrastructure to disseminate to all the schools, they can develop prototypes and they can say, okay, in order to do this activity, each school, we need $50 per school. And then they can raise the funds for that and then distribute that to the schools. So, yeah.
Another question is, I know you're going to be busy, but will you have some TAs or undergraduate students available if I get a TA?
Yeah. So the idea is similar to working as a facilitator. So you should ask 3 other people before you ask the teacher. So you have your network community. So you have your 5 schools. And ideally, you'll set up some time that you guys can interact. So you may decide, okay, first Monday of the month, we're going to all chime in on a teleconference for 30 minutes or 45 minutes. Or you may send each other emails. If all that fails, then yeah, there'll be office hours that I'll have. I was planning to have maybe 1 hour, maybe every 2 weeks. And basically you can check in on stuff. And you can always send me email. It's just a question of how quickly I can reply. I may decide to delegate it to some of the student assistants to answer or to try things out. Like you say, oh, I did this activity and this didn't work because this, and we think there's something broken. And then I was like, oh, okay. So then we have our students here who test it out, and if they find the same thing, then we come up with some solution for you.